All right, so with chapter 3, we're going to start to look at chemical reactions. We'll get the basics of chemical equations, see different types of reactions, as well as the math that we can use to, in some cases, determine how much of a product we're going to wind up with, how much of a reactant we need, as well as just the math that we can do with individual formula of certain compounds and molecules. All right. And then when we're looking at these chemical reactions, the one thing we always want to keep in mind is that the reactions themselves are never going to be creating or destroying any matter. We're simply just going to be taking those atoms we have, breaking and forming bonds to create new substances. But the atoms themselves aren't going to change, and the amount of matter isn't going to change either. And that's just what we're looking at with the conservation of mass. And then with these reactions, we're going to be able to use chemical equations to represent them. So in this case, if you've ever used a Bunsen burner, the reactants, those are going to be what we start our reaction with. The reason we produce the flame in the Bunsen burner is because we're mixing the methane, that's the gas we're running through, with oxygen just in the atmosphere. So that's why if you've ever used one, you can adjust sort of the settings almost of the Bunsen burner to allow more or less of the oxygen in, and that's how you can adjust the flame itself. But because this is going to be a chemical reaction, we're going to be taking these atoms, breaking the bonds. We're going to break the bonds between the carbon and the hydrogen. So carbon's black and then hydrogen's the gray or white one here. So we're going to be breaking those bonds. Same thing with the oxygen molecules. We're going to break the bond between those two oxygens. And then we're going to be reforming new bonds. So we're going to take some of these oxygens, bond them to the carbon to get carbon dioxide. We'll take some of these oxygens, bond them to the hydrogen to get water. But if you look at this picture, we've got 2 carbons, and then on the product side, 2 carbons. We've got 8 hydrogens here. Same thing on the product side, and then oxygen is 8 as well. Because again, with these reactions, we're going to be taking those atoms and rearranging them, but we're not going to be creating or destroying anything in terms of how many of those atoms we actually have. And then, like I said, with these reactions, we're going to be able to use chemical equations to represent what we have. So this is just sort of a graphical one where we're looking at the methane and the oxygen we're starting with, and then the carbon dioxide and the water that we're going to be finishing with. But typically, we're going to write it out with the chemical formulas. And then when we're looking at these, again, you can see the conservation of mass is 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, and then 2 and 2. So we've got 4 total on that side as well. When we're looking at these equations on the right-hand side, or the left-hand side, excuse me, that's going to be where we have our reactants. So those are going to be the substances we start our reaction with. And then on the opposite side, so you can kind of see with the arrow, we're taking these things and converting them into these. So these are going to be the products that we're going to finish that reaction with. So for the case of the Bunsen burner, we're going to be producing carbon dioxide and water vapor. But with these reactions, we can also specify what state that we do have those substances in. So if you think about water, typically you're going to think of it as a liquid. But in this reaction, we're actually going to be producing gaseous water. So we're going to be producing water vapor. And that's why we're representing it with the G here. Depending on the reaction, the state of matter can play an important role, especially in the rate of the reaction. So it is going to be important to have these specified. And then with it, the gas and the solid, I think, are pretty straightforward. It's a gas or a solid is just going to be the gas or the solid. But what we also have is liquid, and then AQ for aqueous, and these are not going to be the same thing. So with the liquid, if we've got an L as the subscript for one of these substances, what that means is we've got that pure substance as a liquid. So we've either taken the solid version of it and heated it up above the melting point to give us a liquid, or we've cooled down the gas below the boiling point to get us a liquid, but it's going to be that pure substance. Whereas if we have aqueous, if we have AQ, aqueous, if you just think about the beginning of the word, kind of sounds like aqua, because aqueous is going to be referring to taking that substance and just adding it to water to create a solution. So a simple one would just be sodium chloride, NaCl. We would have that as AQ, because that means we took some of that solid sodium, sodium chloride, added it to water, and just created a salt water solution. Whereas if we had NaCl as a liquid, that means we'd have to heat it up above the melting point, which is just going to be not something we really ever see, because the melting point is going to be like 1400 degrees Celsius or 2700 degrees Fahrenheit. So it's going to be extremely, extremely hot. That's why if you ever cooked anything with salt on it, as you're cooking it, the salt doesn't just start to melt, because the melting point is going to be extremely, extremely high. So we're going to have two very different substances if we had sodium chloride as a liquid versus sodium chloride as an aqueous solution. And then also with these reactions, like I was saying before, we're always going to conserve mass. So whatever we start the reaction with, we have to finish the reaction with. But if you look at this one, if we just had CH4 and O2, we would only have 2 of oxygen. So if we just ignore the 2 out in front here, whoops, we wouldn't have the balanced reaction. So that's why we're going to have these coefficients in some cases. This is going to, as you can see with the picture here, represent 2 molecules of oxygen now for every 1 molecule of methane. Because if we just have 1, we don't have to write it in, kind of like with carbon here. Since we just have that single carbon, we don't have to write in the subscript for 1. It's just assumed to be 1 unless it's otherwise stated. So in this case, we've got 1 molecule of methane plus 2 molecules of water, giving us 1 molecule of carbon dioxide and 2 molecules of water. And with those, it's going to be important that if we're trying to balance a reaction, we use the coefficients rather than the subscripts. So if we're thinking about a reaction that has water in it, and maybe we need to get 2 oxygens on that side of the reaction, what we have to do is use the coefficient. So in that case, we'd have to put a 2 out in front, because that would give us 2 water molecules. If we came and added a subscript here, so if we wanted a second oxygen on this side, we would have to use the 2 out in front like here. We wouldn't be able to add a little 2 after oxygen, because now if we change this formula, we're going to be looking at a completely different substance. So if we had a 2 after the oxygen here, now it's not water, now it's going to be hydrogen peroxide, which is going to be a completely different substance. So whenever we're trying to balance these, just remember we can't change the formula, we can only add the coefficients. But when we have those coefficients, it's essentially just going to be multiplying everything in that structure, or in that formula. So in the case of 2H2O, now this means we've got 2 of those water molecules. So we're going to have 4 hydrogens, because each of them are going to give us 2, and we're going to have 2 oxygens there. So again, if we add the subscript to get a second oxygen, now we have hydrogen peroxide. So we have to add the 2 out in front to say we've got 2 of those water molecules now. And then with these reactions, we have to balance them in order to conserve mass, like we've been talking about. But what we're also going to see in some cases is we're going to have to balance them to make sure we have the same charge on both sides. So if we go back for a second, oops, let's go back more than I thought. With this reaction, we don't have a charge on any of these substances, which means everything on the left, everything on a reactant side is going to be neutral to start. Same thing with everything on our product side. So we're conserving mass, but we're also conserving charge. But if we ever have a reaction where one of these is maybe negatively charged, so if we had a -2 on this oxygen, now we would have -4 total, because it'd be 2 times that -2. So we would need to conserve that charge. We would ultimately need to have a -4 charge on the right-hand side as well. So in addition to the mass, we're also going to have to conserve the charge in these reactions. So with it, if you want to go ahead and kind of practice with these quick, you'll be able to. I would just recommend kind of pausing the video, because I'm just going to kind of click through the answers, and then we'll see how we can kind of set one of them up on the next one. So if you want to try to practice with these on your own, you just want to kind of pause it. But what you're going to want to do, or at least what I would recommend you do, is for each of these reactions, and we'll see it on the next slide, but I think the answers will actually pop up first. With each of these reactions, you're going to want to make a table so that we can keep track of how many atoms of each of these different elements we have. So for the second one, for instance, we would want to have nitrogen and hydrogen, and then we've got two of each of them on the left, but we've only got one nitrogen on the right. We've got a third hydrogen there. So we want to use that table. So as we go through and add these coefficients to try to balance the reaction, so you can keep track of everything you have. With this second one here, you may be able to kind of do it just in your head because it's only two elements. Same thing with the third one. But as we get more elements, especially in some cases, we're going to have to kind of go back and forth, and we may even have to change one of these coefficients multiple times just to keep track of everything, make sure it's all balanced. It's going to be easy to kind of lose that. So again, if you do want to practice with these, just pause it. But what we're going to see is just see the answers here. So, and then with the next one, we'll see how we can actually get these. But for the first one here, and actually I'll save this first one because we'll see that one on the next slide. But with the second one, again, we had two hydrogens, two nitrogens on the left. We didn't have either of those balanced on the right. So we needed a second nitrogen here. So that's why we add the coefficient out in front, gives us two of those nitrogens. But it's also going to give us 6 hydrogens now. 2 times 3 gives us 6. So that's why we have to go then back to the left and add the 3 here. And then with the next one, again, kind of the same idea. We've got 4 phosphorus on the left. So we need a 4 in front of the PCl3. That gives us 4 phosphorus. And then with that, now we have 12 chlorines. So we have to go back to the other side. Each of these molecules for chlorine gives us 2. So that's why we would need 6 molecules in total. So 6 times 2 gives us 12. 4 times 3 gives us 12 as well. And then with the third one here, in this case, what do we have? We've got oxygen, 1 and 2. So 1 on the left, 2 on the right. Chlorine, 4 on the left, 1 on the right. And then silicon's balanced. Hydrogen, 2 and 1. So there's a couple of different elements we actually need to balance in this case. So there's a couple of different ways you could start it. What I would probably do is add a 4 in front of the HCl, balance the chlorines. But that gives us 4 hydrogens then. So we're going to need to go back, put a 2 in front of hydrogen, or 2 in front of water, excuse me, to give us 4 of those hydrogens. And then with that, that'll also give us a second oxygen on this side, which balances the 2 oxygens we have there as well. And then with the final one, in this case, a couple different ways we could start it again. With it though, since we've got a single element by itself, same thing with nitrogen, but since we've got copper completely alone, what I would recommend when you have a case like this where you've got a single element by itself on one side of the reaction is focus on that one last, because what we'll be able to do is at the end put whatever coefficient we need for copper here, and we'll be able to balance the copper then, but it won't change anything else. If we then add a coefficient in front of anything in this formula or this formula, now we're going to be changing multiple elements. But with something like copper here, we can only affect its, or we can only change that thing. So if we need to at the end, that'll be the easiest one to kind of balance. So with this one, what I would do is probably put a 2 in front of the ammonia here, balance these 2 nitrogens. But that's going to give us 6 hydrogens now. So if we have a 2 here, we can do it. We've got a 2 here. Now we've got 6 of these hydrogens. So we need to go to the other side, put a 3. That'll give us 6 hydrogens as well. But now we've got 3 oxygens. So we've got to go back to the other side, put a 3 there to balance the oxygen. And now we've got 6 coppers. But now when we go to the right, we can put a coefficient here without changing anything else. So we can correct the copper, but since there's no other elements here, we're not going to wind up throwing off anything else. All right. And then to see how we can kind of do the first one, what I mean with the actual table here is for each side of the reaction, I would just make a table so we can keep track of everything we have. And the reason I picked this one to focus on is because in this case, we've got a polyatomic ion, and we've got that exact same polyatomic ion on the other side of the reaction. So CO3, the carbonate ion, is the exact same on both sides. So when you've got something like this, when you've got one of these polyatomic ions and it doesn't change from the left to the right, of course, we're changing what it's with, going from potassium to hydrogen. But the polyatomic ion itself is still staying intact. We can, instead of splitting it into carbon and oxygen, we can treat it as CO3. But again, we can only do this because it stays intact. If the carbonate that we start with winds up decomposing into something else, then we have to split it as carbon and oxygen. But since we have CO3 on both sides, we can just do the same thing. And then with this, when you make the table, make the table on both sides of the reaction, and then keep everything in the same order. So when I made the table on the left side, I just went in the order that we had those different pieces. So I'm calling them pieces in this case, because again, we've got the polyatomic ion for CO3. But when you go to the other side, don't list them in the order they are in the reaction. List them in the same order you had them on the left, because now we'll be able to just look directly across and compare those easily. Whereas if I come through and put potassium, chlorine, hydrogen, and CO3, now we're going to have to crisscross a few of those, and it's just going to make it a little bit more difficult on ourselves. So just keep the table in the same format on both sides. And then we just want to keep track of everything we have. So on the left, we've got a single hydrogen, a single chlorine, 2 potassium, and 1 carbonate. And then for this one, we've got all of these pieces just in a single spot. But in some cases, you'll see we may have oxygen in 2 different formulas. So you just want to make sure that you're keeping track of everything on those sides of the reaction. But now on the right, we've got 2 of these hydrogens. We've got 1 chlorine still, 1 potassium now, and just 1 carbonate. So in this case, there's 2 different things we need to balance, hydrogen and potassium. So when we go to actually balance it, we could start in a couple different points. We could put the 2 in front of KCl. We could put a 2 in front of HCl. Ultimately, it's going to be the same thing, because when we put the 2 in front of KCl on the right, now that gives us the second potassium we need, but it's also going to give us a second chlorine. So then when we go back to the left, we can put a 2 in front of HCl, and that'll give us the second of both of those atoms that we need, both of those elements. So again, with this table, just make sure as you go through, this one's a relatively simple one, but as you go through, just make sure whenever you add these coefficients, because remember, we can't change the formula, as you add these coefficients, update your table, and update your table for every element in that formula. So for this one, when we started, we put the 2 in front of KCl because we wanted a second potassium. But since we also had chlorine in that formula, that's why we had to update Cl as well. But if you kind of do that, do this process, again, it may be a little bit more complicated in some, where we kind of got to go back and forth. In some cases, we may need to change a coefficient a second time, just in order to balance it with the other changes we make. But if you can just keep track of your atoms in the table, you'll always know exactly where you are. And then the final piece you'll also want to do is just double check to make sure that these coefficients can't be reduced. So in this case, and in any case where we've got a coefficient of 1, that's going to be the simplest we can have. But just make sure we can't reduce these coefficients at all, because in this case, you could wind up with, whoops, I'm trying to draw 4 there. You could wind up with 4, 2, 4, 2, and it's still balanced. We would still have the same thing. We'd have twice as much of everything. But with these balanced reactions, we want to have them in the simplest ratio. So that's why if you do ever have something like this, you just want to double check it. And if you had 4, 2, 4, 2, we would just want to divide everything by 2. So if you ever have all even numbers, that's a definite that we can reduce it. But there may also be cases where you've got like factors of 3 or factors of 5 or something like that. So you always just want to double check, make sure we can't reduce those subscripts further. And then with these reactions, we're going to have a couple of different types of reactions that we're going to look at. And these aren't going to be an exhaustive list. There are other reactions, and we'll see those throughout the later parts of the course. But the 3 that we're going to focus on are going to be combination, decomposition, and combustion. So combustion, we've actually already kind of seen with the Bunsen burner equation. That's essentially just going to be burning something in the presence of oxygen. And then with combination and decomposition, we'll see that those are essentially just the sort of the reverse of each other. Because with these combination reactions, as that name would suggest, and sometimes you may see it called a synthesis reaction. But with these reactions, what the key piece is going to be is that we'll have a single product. So in this case, for all three of these reactions, we just have two reactants. We could have three, we could have four, we could have any number of reactants, as long as it's more than two. But the key identifier is going to be that single product. We're going to be taking all of these reactants, combining them into one product. And that's going to be the key identifier for these ones. So it's something like the first reaction here. So if you actually perform this reaction, you can kind of see it a little bit in the second picture here. So they're showing how the reaction is going to take place. Magnesium plus oxygen gives us that new substance, magnesium oxide. But you can kind of see it with the bottom of this picture here. This reaction is going to produce a very, very bright white light. So it's going to actually give off some ultraviolet light. But what we're going to finish the reaction with is, instead of a shiny metal, we're going to have kind of a crumbly white solid there. So that magnesium oxide. And then with combination reactions, so with it, these are all just examples of metal plus oxygen. So that's why we're creating a metal oxide. So magnesium oxide or strontium oxide, sodium oxide. And then when we take metals and react them with water, we're going to have metal hydroxides. So these are actually going to be bases here. We got that basic hydroxide. But the reason we're considering metal hydroxides now: magnesium hydroxide, strontium hydroxide, sodium hydroxide. So those are all the metal with that hydroxide piece. And then, again, there's still a combination reaction, because we're taking multiple things and just creating that one substance as our product. And then, like I said, the decomposition reactions are essentially just the reverse. So that's why in this case, we're starting with one substance, breaking it down into multiple pieces. So in this case, we're taking water, splitting it into the individual elements, hydrogen and oxygen. We're taking calcium carbonate, breaking it down into calcium oxide and carbon dioxide, or the similar reaction with potassium chlorate. We're decomposing it into potassium chloride and oxygen. So if you've ever taken a biology course or something like that, you may have talked about decomposers. So if you like a leaf falls off a tree in the autumn, the decomposers, those microorganisms, break it down, release those nutrients back into the soil. So we're taking that larger substance, breaking it down into the smaller pieces. Same thing we're seeing here with these decomposition reactions. So we're taking something like water, splitting it into hydrogen and oxygen. And then again, with all these reactions, you can see we're conserving mass. So that's why we've got the coefficients in some of them. For the second one, we've got one calcium, one carbon, and then three oxygens. So in this case, the oxygens are split between those formula. So we don't actually need the coefficients there. But in the case of the first one, two water molecules gives us two hydrogens and one single oxygen molecule. And then with this should just be the arrows. They, for some reason, just got formatted weird on this slide. But when we're looking at carbonates, so CO3 with the -2 charge, so calcium carbonate, copper 2 carbonate, magnesium carbonate, when we decompose those, what we're going to see is that they're going to break down into the metal oxide and carbon dioxide gas. So we're basically going to have one of the oxygens stick around with the metal, and then the others are just going to be part of the carbon dioxide there. And then with combustion reactions, we're going to primarily limit it to hydrocarbons, so substances with carbon and hydrogen. Sometimes we'll also see carbohydrates, so things that also contain oxygen, so CHNO. But the key piece with these is that we're going to see some formula that looks something like this. So the amount of carbons, the amount of hydrogens may differ. But then we're going to be reacting it with oxygen. So that's why if you've ever been burning a candle and you put the lid back on, the reason the flame ultimately goes out is because when we put the lid on, we're cutting off the supply of this oxygen. So we're effectively removing one of those reactants, and now we're just left with the hydrocarbon. And we need both of these pieces in order for the reaction to occur. So since we're removing the oxygen, essentially, that's why the flame goes out. So that'll always be one of the reactants. And then with the products, we're always going to have carbon dioxide and water. It's just depending on what substance we're burning, we're going to wind up with a different ratio of these. So you can see very similar formulas here, just 3 carbons versus 1, 4 hydrogens versus 8. And that's why we've got different coefficients. Sometimes we may have a coefficient in front of the hydrocarbon as well, but that's going to be pretty much the only piece that changes is basically how we balance these. Because the 75% of this reaction, oxygen going to carbon dioxide and water, is always going to be the same, except for the coefficients. And then, of course, that's going to be, like I said, dependent on what substance we're actually burning. And then with these reactions, the formula is going to be extremely important. That's why, like we were looking at when initially balancing them, we can't change the formula because that changes the substance. But we're going to be able to use these formulas to ultimately help us determine if a reaction is taking place, how much of a product is going to be produced, how much of a reactant is going to be needed for whatever we ultimately want to do. And when we're first looking at these, we're going to look at them in terms of formula weights, or sometimes they're called molecular weights. But with them, we're going to be looking at them with the unit AMU, so atomic mass unit. And with it, we're not going to know which isotope we have. So we don't know what isotope of calcium. We don't know what isotope of these chlorine atoms we're going to have. So that's why we're going to use the decimal values from the periodic table. So depending on what periodic table you use, you might wind up with slightly different values here, but it's going to be the same process. So if we want to determine the formula weight, essentially how much does a single molecule weigh, what we're going to do is just look at that formula, look at what elements we have and how many of them we have, and then just basically add those pieces up using the periodic table. So for calcium chloride, we've got 1 calcium. And if we look at our periodic table, we're going to see that it's just barely over 40. And then the same thing with the chlorine, but in this case, we've got a second chlorine. So 2 times, and then chlorine is a little bit over 35. So that's when we add up all 3 of those atoms, 2 chlorines, 1 calcium, we get 110.984 atomic mass units. And again, this is going to be if we're thinking about just a single molecule of this substance. We can do the same thing with something like ethane. And in this case, we've got 2 carbons, so a little bit over 12 each, gives us 24 coming from carbon, a little over 24, I should say. And then hydrogen, we have 6 of them in that formula, a little bit over 1. So we're winding up with just over 6 from the hydrogens. And when we combine them, we wind up with just barely over 30. And with it, I would recommend you use a table like this where we kind of separate it into those individual elements, look to see how many of them we have, how much each of those atoms weigh, and then just add them up to the right-hand side there. And the reason I would recommend you do that is so that you can, when we get to the next piece, when we're looking at the percent by mass, if we do it like this setup, we'll already have the part. So if we wanted to figure out percent carbon, we'll always have already have the mass from carbon, and we'll already have the mass of the entire molecule. So we'll have all the pieces we need if we set it up like this. But you can go ahead and practice with the examples here. And then again, what you're going to want to do is just look to see how much each of these atoms weigh, factor in how many of them we have, and then just add up all of those pieces. And then with these ones, since we've got these parentheses here, similar to math, what we're going to do is just take that number on the outside and just distribute it to everything within. So for the first one, copper 2 nitrate, Cu parenthesis NO3, and then the 2 on the outside. That means we just have one copper, but this 2 on the outside of the parenthesis gets distributed to everything on the inside. So instead of NO3, we really have 2 nitrogens and 6 oxygens. And then similarly with the second one, zinc hydroxide, what that means is we're going to have that single zinc out in front, but we're going to double everything on the inside of those parentheses since we've got a 2 on the outside. So now we're going to have 2 oxygens and 2 hydrogens. So when we look at adding all those up, what we should see is 187.57 for the copper 2 nitrate, and then just under 100 for the zinc hydroxide. And then again, depending on what periodic table you look at, you may see a slightly different answer just because the values on those atomic masses are going to be rounded to different digits. So sometimes you have 2 decimal places, sometimes you'll have 3. But depending on the periodic table, that's why you just may see slightly different numbers there. Okay. And then like I was saying, with it, I recommend using kind of a table format so that if we want to determine what the percent by mass for any of those elements are, we'll already have that information. And then with percentage, so percent composition, we're looking at percent mass, what percentage of that molecule is going to be from a certain element. When we're looking at it, it's always going to be part over whole. So anything percentage is part over whole. So if you think about a test score, it's how many points you got over the total available points times 100 just to make it a percentage. So in the case of percent composition, it's going to be on the bottom, the entire thing. So the whole will be the mass of the entire compound. Whereas the part is just going to be whatever piece we're interested in. So if we have our table, if we go back for a second to this one, if we're looking at part copper or part hydrogen, that would be the 24.022 for carbon or the 6.0474 for hydrogen. And then the whole is just going to be the 30.069. So if you've already got the table set up like this, we just need to look at what element we're interested in, and then the entire thing, divide those two, and then just multiply by 100. Yeah, so if we do look at this example, if we want percent carbon, like I said, 2 times 12, that's the 24 we had. So we'd wind up with just under 80%. And then if we also wanted hydrogen, we could go through and do the math here. So it's the same thing. It's just the only part that's different is we want to focus on hydrogen. But with this one, remember the percentage is going to have to add up to 100. So if we know all of the pieces but one, so in this case, if we know just one of the elements, we can know the other because we can just do 100 minus whatever that first one is. So in the case of hydrogen, we would do 100 minus carbon. So we do 100 minus 79.89, and would give us 20.11. If we had 3 elements here and new carbon, we would still have to do the second one. But then we could add up those two and get the third. So if we also had oxygen in this one, we could get the percent carbon, but we wouldn't be able to just automatically know hydrogen. So we'd have to find this one. But since everything would still have to add up to 100, if we knew these two and had oxygen as well, we could figure out whatever that would have to be. Of course, one of these would have to be lower in that case, since they already add up to 100. Okay, so if you want to practice with this one, you can just pause it. Pause it. But I'm just going to sort of quickly go ahead and show how we would set this one up. And I actually didn't write down the answer for this one. But we've got for carbon, hydrogen, oxygen. So each oxygen will be 16.00, which will be 96. Each hydrogen, we've got 12 of them, but each hydrogen is 1.008. So that's going to give us a mass of 12.096. And then each carbon is going to be just a smidge over 12, 12.01. which is going to give us a total of 72.06 there. So when we add all of these up, we should get 180. And then if we're looking at the sig figs, we've got 2 of them. After the decimal, we're adding these up now. 2 of them for oxygen and carbon, but 3 of them for hydrogen. So we're just going to round up to 0.16 at the end rather than 0.156. But this is going to be the mass of the glucose molecule. And now if we wanted to get the percent of any of these individual elements, if we wanted carbon, we could do 72.06 divided by the entire thing times 100. Or the same thing with hydrogen or oxygen. We would just want to make sure that we're using the part for that element. So 12.096 on top for hydrogen, or 96 on top for the oxygen. But with it, I forgot to write down the answer for that one, so I don't actually have it. But it's going to be just a little over 50% for the oxygen. 72, so what'll that be? It'll be a little bit under, so probably like the high 30% maybe there. And then this maybe like 7. But again, whatever it's going to be the part, so that mass of the element over the whole, so the mass of the entire compound times 100. Okay. And then when we're working with these substances in the lab, for instance, we're not really going to have just a single molecule or a single atom of anything ever. We're going to have a much larger sample. And even if we just have a half of a gram of something, there's going to be millions and billions of molecules in that sample. So instead of using the formula weight or the molecular weight, what we're going to be using is the molar mass. And when we're looking at that, we've got the mole, which is going to be a very similar concept to dozen. But a mole, instead of where a dozen is equal to 12, a mole is just going to be equal to Avogadro's number, which is going to be 6.02 times 10 to the 23rd. So if we had one single molecule of water, for instance, that oxygen is going to be 16. Each hydrogen will be just over 1. So we'll wind up with, if we round it, we'll wind up with a molecule that's 18 AMUs. But now if we've got 1 mole of that, we've got 6.02 times 10 to the 23rd molecules. So the mass of that sample now is going to be the same number, but we're going to change the unit to grams. And then the way they kind of determined this is this number, Avogadro's number, was calculated based on however many atoms of carbon-12 would be in 12 grams. And then this number refers to 1 mole of anything. So if I had a dozen donuts, I'd have 12 donuts. If I had 1 mole of donuts, I would have 6.02 times 10 to the 23rd. But what the mole is going to be important for is that's going to be ultimately what allows us to relate one substance to another. So if we're looking at a chemical reaction, those coefficients, we can think of them in terms of moles, or we can think of them in terms of molecules like we kind of started with, or we're going to be able to think of them in terms of moles, because they're both going to be effectively just counting how many of those pieces we have. Whereas the mass isn't going to isn't going to be what we are able to relate these substances with, just because each of those molecules is going to weigh different. But when we're looking at the molar mass, like I said, that's going to be what we're actually using rather than the formula weight. The molar mass is going to be that same number. So the way we calculate is going to be the same. Look at the formula, see how many of those atoms we have, see how much each of them weighs, and just add them all up. But instead of AMU, what we're going to have is grams per mole. So it's telling us how many grams of that substance we would have if we had 6.02 times 10 to the 23rd molecules of it, if it's a molecule, or if it's atoms, just 6.02 times 10 to the 23rd atoms. How much would that weigh? So if it's just a single helium atom, for instance, the formula is just going to be He, just because it's not going to react with anything. So in that case, it would be 6.02 times 10 to the 23rd atoms. And with it, we can work through a couple examples here. So in this case, we'll be able to see if we have 5 grams of a substance, in this case, the nickel, how many moles would that be? And then how many atoms would we actually have in that sample? So for the first one, if we're going grams to moles, or if we're going in the opposite direction too, if we know how many moles we have and we want to calculate how many grams that is, we're going to have to use the molar mass itself as a conversion factor. And in this case, just similar to the one with helium I was just talking about, nickel is just going to be that element. The formula is just going to be Ni for nickel. So the grams per mole, the molar mass, is just going to be the atomic mass from the periodic table. We're just going to use grams per mole as the unit rather than AMU. So when we go to set this one up, that'll be our conversion factor is the molar mass. And since we're going to be starting with grams on top, that's why we're going to have to put the molar mass. We're essentially going to have to reverse it. So instead of grams per mole, we want grams to cancel. So that's why we're just going to flip this. And again, this number just comes from the periodic table for nickel. But with this, again, thinking back to dimensional analysis, we were just doing unit conversions going from some distance to another, so centimeters to miles. If we wanted centimeters to cancel, we needed that unit in an opposite spot. It's the same idea here. We're just trying to go from grams to moles. We're still representing the same quantity of that sample. We're just using a different unit to do it. Because grams represents it in mass, moles represents just how many, in this case, atoms we're going to have. But we still need these conversions. We still need the numerator and the denominator of each step to be equal to each other. So what this is saying is for every 58.693 grams of nickel, we have 1 mole of that substance. So when we go through and actually do the calculations, grams is going to cancel. And that's why we'll be left with the moles. But if we're thinking about the significant figures, we've got 3 sig figs in our initial mass. So we should only have 3 sig figs in our final answer. So we're going to round this 1 up to a 2. So 0.0852 moles of nickel. But now if we want to go one step further, we want to determine how many atoms we have. What we want to do is think about what a mole represents. And a mole represents 6.02 times 10 to the 23rd, whatever that thing is. So if we have 1 mole of nickel, we would have 6.02 times 10 to the 23rd atoms of nickel. And that's going to be our conversion factor, because that's going to allow us to go from moles to actual atoms. And in this case, we'll be able to do it just in a single step, because the formula itself is just nickel. So it's just that one thing. If we have a molecule, so something that's got multiple atoms in it, we'll have one extra step or one extra little piece. But in this case, again, the conversion factor, it's just the relationship between moles and atoms for nickel. For every 1 mole of nickel, we have that many atoms. So now if we multiply it by however many moles we actually have, moles is going to cancel, and we'll be left with the number of atoms. But again, we want to focus on the sig figs. So we still just have 3 in our initial amount. So we should have 3 in our final answer, 5.13. So we're going to get rid of the 0 and 1 there, just to round it to 3 sig figs. And then when we're doing these conversions, we're going to be going in all kinds of directions. So sometimes you need to go grams to moles. Sometimes you may need to go one step further to the formula unit, which we'll see in a little bit in a little table. Could be a couple different things. But when we're doing grams to moles, or the reverse direction, we're going to be using the molar mass. So it's going to be coming from the formula, coming from the periodic table. Whereas if we're going moles to number of atoms or number of molecules, whatever it's going to be, we're going to be using Avogadro's number in that case. And the same thing if we're going in the opposite direction. So if we look at one more example, if you want to practice with this one on your own, you can. But how many grams are present in 3.40 moles of nitrogen? So in this case, we're going from moles to grams. We're going to be using the molar mass. It's going to be slightly over 28 for nitrogen, since we got 2 of those nitrogen atoms now in this formula. So when we set it up, in this case, we're starting with moles. So when we use our conversion factor, we want moles to be on the bottom. And that's why we've got grams on top here. Moles will cancel, and we'll just be left with the number of grams we'd actually have if we had 3.4 moles of nitrogen. But again, 3 sig figs should have 3 sig figs. So we're going to round this to 95.2 grams there. And if we want to figure out how many copper atoms are present in 15.0 grams, it's going to be the same idea. We'll use that conversion factor, we'll use the molar mass first, because we're starting in grams, we have to go to moles. And just like nickel, since this formula is just that element by itself, we can just get the number from the periodic table. Grams will cancel since we put grams on the bottom now. We'll be left with moles. And it'll wind up being 0.236 just to match the sig figs. But now if we want to go one step further, we want to figure out how many atoms there actually are. Now we'll have to multiply it by Avogadro's number. Oops. And then, and for this one, what's happening is, since this is really just one equation or one problem, we really could do this in one single step. So we could put this immediately after and just do it in one calculation. So we wouldn't actually want to round this number here. And that's why with the setup, we're not actually using the correct number of sig figs in this step, because with it, we don't want to round it in the middle of our calculation. So since we can really just do this in one string of steps, that's why this number doesn't have the correct number of sig figs. But when we look at our final answer, we want to make sure we're accounting for sig figs. So since we had 3 and 15 grams, we should have 3 in our final answer. So 1.42 is the 3 sig figs. And then the 10 to the 23rd just gets us to the correct scale there with the scientific notation, because we really could write this as 142 and then 21 zeros afterwards. All right. So now with this one, we want to figure out how many atoms we have. But in this case, we've got a molecule, and we want to figure out specifically oxygen atoms. So since we're given moles, we can kind of start heading in that direction right away. We don't have to use the molar mass at all. If we were told we had 112 grams or whatever it's going to be, then we'd have to convert to moles first. But since we're already in moles, we can start working towards the number of atoms. But with it, we can't go directly to oxygen atoms, because if we've got moles of oxygen, we first have to figure out how many molecules that's going to be. So that's with the formula unit here. You can really think of it as 5.32 moles of calcium carbonate, which is just chalk, also used in antacid. But 5.32 moles of that substance, moles is going to cancel, and we'll have 6.02 times 10 to the 23rd molecules of that substance for every 1 mole. So when we solve it, 3.20 times 10 to the 24 molecules. But if we want to figure out how many atoms we actually have for oxygen, we got to go one step further. And basically for every 1 molecule, that's what we're referring to as a formula unit here. For every 1 molecule, we're going to have 3 oxygen atoms. So that's why this number is just going to get tripled. So we should wind up with 9.60 times 10 to the 24th. With it, we really could simplify this and make it in one step. We could do 5.32 times, and then Avogadro's number times 3, since we could just look to see how many atoms of oxygen per every molecule. So you could kind of combine these into one single step if you wanted to, but you can break them down into 2 if it's a little bit easier to see molecules or moles to molecules, and then molecules to oxygen atoms. If we're looking at calcium or carbon atoms, since we have one atom for every molecule, we basically could stop after this first step, since we would just have 1 on the top of the second one. So it would just be that same number times 1. But if we wanted the total number of atoms, then we could do the same thing, figure out how many molecules. But for the top piece here, now we would want 5 atoms, because we've really got 1 calcium plus 1 carbon plus 3 oxygen. So if we wanted total atoms, we wouldn't specify one specific element, and that's why we'd have 5 total on the top. So we'd wind up with a slightly larger number there. And then with this mole calculation, the uranium used in nuclear fuel exists in nature in several minerals. Calculate how many moles of uranium are found in 100 grams of carnotite. So this is going to be the version of uranium we have here. And if we start with 100 grams, there's a couple of different ways we could approach it. If we start with 100 grams, and then they're using Ca just to represent carnotite, which isn't the best because it is really calcium. But that's going to be what we're referring to this version of the uranium molecule as. We can figure out how many grams total we're going to have. So we can use that molar mass that's given to us. MW for molecular weight, same kind of idea as molar mass. So just if we add up everything here, it's going to be kind of annoying since we've got parentheses and a whole bunch of stuff. But if we did, we'd wind up with 902.18 or 1758, excuse me. So we can convert that to the number of moles of that substance. And now this is the total number of moles. We then can use that to figure out how many moles of uranium we're going to have. Because if we look at the formula, we've got 2 uranium atoms for every molecule. So remember, mole is essentially just counting. So if we have 1 mole, we'd have 1 mole of this substance. We'd have 2 moles of uranium, because for every 1 molecule, we get 2 uranium atoms. So we can essentially just then double this number. And then if we wanted the actual number of uranium atoms, we'd have to go 1 step further and multiply by Avogadro's number. So we'd have 6.02 times 10 to the 23rd on top for uranium atoms. And then we'd have 1 mole of uranium atoms on the bottom. So that would give us the actual number. And then just to look at the mole relationship here, with the first one, if we're looking at atomic nitrogen, that means we've just got that single atom. So the weight of it would be 14, depending on if we're looking at a single one or a mole's worth. The units will change from AMU to grams per mole. But that means we'd have 6.02 times 10 to the 23rd atoms of nitrogen. But now if we're looking at molecular nitrogen, so the nitrogen that exists in the atmosphere, it's like 70% of the atmosphere. Now we've got 2 of those nitrogens triple bonded to each other. So that's why the mass here have doubled. And if we're thinking about the relationship, that means we're going to have 6.02 times 10 to the 23rd molecules, because now we've got 2 of those atoms together. So if we had a mole of molecular nitrogen, we would have that many molecules, which means we would have twice as many nitrogen atoms, because we're getting 2 of those atoms for every 1 molecule. And then kind of the same idea with this bottom one here, barium chloride. If we had 1 mole of barium chloride, we would have 6.02 times 10 to the 23rd molecules of that substance. And then since we get 1 barium ion per each of those molecules, we would have that same number of barium ions, but we get 2 chlorines for every molecule. So we would have twice as much of the chloride ion. Yeah. And then what we're also going to be looking at with these formulas and with these percent compositions is how we can determine what the empirical formula or what the molecular formula is going to be based on those percentages. So with this one, we're looking at tin 4 oxide. And with it, if we know the name of it, we could get the formula. Whoops, it's not the pen. Because tin 4 means tin, SN, is going to have a positive 4 charge. Oxygen, -2. So when we do the crisscross method or think about how these are going to have to combine, we've got a positive 4 for the tin, so we'll need a -4 from the other piece. So that means we'd really need 2 of those oxygens. So the formula is going to be SnO2. And what we're going to be able to see is if we had the percent mass of these elements, we'd be able to determine that same formula, even if we didn't know the name of it already. And the way we're going to be able to do that is essentially treat each of these as a percentage, and then think about how many moles we're going to have, and you look at the relationship there. So the way we're going to do this is, if we have the percentages, we're just going to assume we have a 100-gram sample. and then change each of those percentages directly to grams. So if we had 25% carbon and 50% oxygen and 25% hydrogen, if we had a 100-gram sample, then we'd have that many grams of each of those elements. So if we've got these grams, we can then use the molar mass to convert to moles for each of those elements. And then just looking at the number of moles, we can figure out based on the ratio what the empirical formula is going to be. And with the empirical formula, just remember this is going to be the simplest ratio of those elements to one another. So the molecular formula actually tells us exactly how many atoms of each of those different elements we have, whereas the empirical is just the ratio of one to the other. But if we also have the molar mass of that substance, we can then go one step further and get the true molecular formula. And we'll see that with one of the examples as well. So if we look at the example we have here, para-aminobenzoic acid, excuse me, PABA, is going to have a composition of 61.31% carbon, 5.1% hydrogen, just a little over 10% nitrogen, 23.3% oxygen. And we want to get the formula for this substance. So if we convert all of these percentages just to grams, 61.31 grams, 10.21 grams, 23.33 grams, what we're going to be able to do is use the molar masses to figure out how many moles of these substances we would have. And then we're going to be able to use these different moles to get the simplest ratio of one to another. And that'll give us the actual formula. So again, the grams we have here is the same percentages we have. We just changed the units to grams because we're pretending we just have a 100-gram sample of this substance. So if we had 61.31%, that would be 61.31 grams. And then we're multiplying each of those by the molar mass, the inverse molar mass, really, for those elements. So for carbon, 12.01 on the bottom, hydrogen, 1.0079. So again, depending on the periodic table, this may be 1.008, but it's going to be the same process. And then similarly with nitrogen and oxygen as well. And this gives us how many moles of those elements we would have in a 100-gram sample based on those original percentages. And then when we have the formula, the empirical formula, the simplest ratio, we just want to have these moles, because we can think of the subscripts in those formula as equivalent to the mole ratio of those elements. We want to have those just as whole numbers. So what we're then going to do is take the smallest number of moles we have. So in this case, the 0.7288 for nitrogen. We're going to divide all of these numbers by that, because that'll make nitrogen just equal to 1. And then that'll give us the ratio for the others there. So when we do it, we get 7, about 7 for carbon and hydrogen, pretty close. So we're just going to round those. Same thing with oxygen. We can just round that to 2. So you usually won't get exactly the perfect whole number, but we'll oftentimes be pretty close to a whole number like we have here. And that means the empirical formula is just going to be 7 carbons, 7 hydrogens, 1 nitrogen, and 2 oxygen. So in this case, the 7 black atoms they're shown here are carbon. We've got, you can't see the 7th hydrogen, but it's just on the other side of this oxygen, but they're represented with sort of the cream color. And then the 7th one is just on the back here. These 2 reddish orange ones are going to be our oxygen, and then the blue is the lone nitrogen there. So if we look at the steps for this again, pretend that the percentages are just out of a 100-gram sample, so we can convert directly from percentage to grams just by changing the unit. Use the molar masses to get moles. Divide those by the smallest number of moles. And then we'll get the whole numbers there for the subscripts. In some cases, we'll see a couple more examples. We may need to do a little bit more in terms of getting the fractions or the ratio to be at whole numbers. But this is going to be the general process we use. So if you want to try practicing on your own with this one, it's going to be a similar idea. We're looking at determining the empirical formula for asbestos. And asbestos, used in a lot of buildings and things like that, exposure to it can lead to lung cancer. And it's going to be made up of magnesium, silicon, oxygen, and hydrogen. So in this case, we're given the percentages directly for magnesium, silicon, and hydrogen, which means we can add those three up and just subtract it from 100 to get the oxygen. So if you do that, you should get oxygen. Oxygen is going to be equal to 49.21%. But for these ones, if you want to work through them on your own, you can. But it's going to be that same process. We'll take these percentages, divide them by the molar mass for those elements. So magnesium, 28.03 would get divided by 24.31. Silicon, you divide by 28.09, 1.008 for hydrogen, 16 for oxygen. And what we're ultimately going to see is that the empirical formula you should wind up with when you go through this process is going to be magnesium 3, silicon 2, hydrogen 3, and oxygen 8. When you get the molar masses initially and then divide by the smallest number, silicon is going to be your smallest, 0.769 moles when you go through this process. When you divide everything by that number, you're going to get 1 for silicon, you're going to get 4 for oxygen, but you get 1.5 for magnesium and hydrogen. But again, we want these to be whole numbers. So since we got 1.5, 1, 1.5, and 4, what we want to do is just think about, based on this ratio, what we can do, what factor we can use to get these to be whole numbers. So anytime you've got a half, just multiply it by 2. So multiply everything by 2. That makes these decimal values 3. And then it just doubles the other ones as well. So we get 2 for silicon, 8 for oxygen. If you wind up with something that's 1.33 or 2.67, it's the same idea. It's just those are going to be factors of 3. So you want to multiply by 3 instead. Same thing if you ever have anything that's a quarter, 0.25 or 0.75. You'll just want to multiply by 4 there. And then when you do those, definitely just double check, make sure you can't reduce it any further. Just make sure that you didn't multiply by maybe the wrong factor or something like that. So for something like this one here, this one we're actually looking at, 1.51, 1.54, you could multiply these by 4 to get all whole numbers, but then we'd have 6, 4, 6, and 16. So we could still reduce those. So you just want to double check that the empirical formula can't be reduced any further. And then for this one, we did have the formula, so Mg3Si2H3O8. So we would also, since we have the actual molecular or molar mass here, we would actually be able to get the molecular formula as well. We'll see that one in a little bit, but it's essentially just comparing the molar mass for the actual substance versus the molar mass for the simplified empirical formula. And what we would see with this one in particular is that the empirical formula, the mass of that one would add up to 260.13, which is exactly half of this one. So in order to get the molecular formula, we would just have to double everything. So we would really have 6 magnesiums, 4 silicon, 6 hydrogens, and 16 oxygens. But the empirical formula, that simplest ratio, would still be the reduced version of it. And then with the next one, same idea. So this one I'll actually go through a little bit. But carbon, oops, no, carbon's not. So carbon 40.92 divided by 12.01. And that gives us 3.4. Sorry for the poor handwriting here. And again, if you want to work through the rest of this one, you can do so on your own. Just pause it, give yourself a little bit of time. But it's going to be the same process where we just first assume the percentages are out of a 100-gram sample. So we can just divide by the atomic, the masses on the periodic table to get the number of moles. So 3.41 for carbon, 4.544 for the hydrogen, and then oxygen 54.5 divided by 16 is going to give us 3.406. 406. So what we can do, divide each of these, actually, so we're going to be dividing all three of these by the same number, so I'm just going to write it like that. And what that gives us is 1 for each of carbon and oxygen. And we're going to wind up with 1.33 for the hydrogen. So we're really just going to have to triple all of these. So we'll wind up with 3 for carbon and oxygen, and 4 for the hydrogen. So we should wind up with C3, H4, O3 there. And again, that's going to be the empirical formula. It's going to be the simplest ratio. In this case, since we don't have the actual molar mass, we don't know, we can't say for certain what the actual molecular formula is going to be, because we don't know what factor we're going to have to kind of scale this up by. So for the previous one, the molecular weight or the molar mass was twice as large as the empirical formula would have been. So we were able to just double everything. In this case, we don't know what that ratio is going to be. We only know the simplest ratio of these elements to one another. And then with the final one here, same idea. If you want to practice with this one again, just kind of pause it and allow yourself to work through it. But it's the same idea. We've got carbon and hydrogen, which means oxygen is going to be, what percentage will that be? 31.55. And again, that's just from 100 and then subtracting the other two. So oxygen just has to be that missing piece. So when we take these percentages, convert them to grams, what we're going to see is that the number of moles that would be is going to be 5.26 for carbon, 5.26 for hydrogen, and then 1.97 for the oxygen. So we're going to divide all three of these by 1.97, and we're going to get a decimal value that's not really close to a whole number. So this is too far away to round right to 3. So if it's like 2.9 something or 3.0 something, then we can round it to 3. But in this case, that's not really close enough to just round it to the whole number. So we again have to think about what factor we can use to get these to be a whole number. And 2.67 is really the same as 2 2/3. So we're just going to want to multiply this by 3. And that means we're going to get 6. We're going to get 8, excuse me, for carbon and hydrogen, which means we're going to have to triple oxygen as well. So we should wind up with C8, H8, O3. And then with this one, this is again the empirical formula, the simplest ratio. We now have the actual molar mass as well. So what we can do is do the actual molar mass divided by the empirical molar mass. And then whatever that factor is, that's what we've got to multiply this formula by. So for the asbestos one, the actual molar mass was twice as large. So everything got multiplied by 2. In this case, if we add up 8 carbons, 8 hydrogens, and 3 oxygens, we're going to get this number. So in this case, this actually represents the empirical and the molecular formulas. Both of those are going to be the same thing for vanillin. But that'll be where we pause the notes for this chapter, and then we'll pick them up in the next video.